Welcome back. So we're going to keep going with the 2009 AB FRQs, starting with question 3. So I have a cable company that's manufacturing cable that sells for $120 per meter. For a fixed cable length, the cost of producing a portion of cable varies with its distance from the beginning of the cable. They report that the cost to produce a portion of the cable that is x meters from the beginning is 6 square root x dollars per meter. We're also told that profit is the difference between the amount of money received by the company for selling the cable and the company's cost of producing the cable. So the first thing we need to do is figure out how much their profit is on the sale of a 25 meter cable. So I'm going to use their little hint here. So let me underline really quick. They told us that profit is the amount of money received by the company, the difference between that and the cost of producing the cable. So money in minus money out is going to be the profit. So if I use that, profit equals, two parentheses just to make this money in minus money out. So the money you receive minus the cost of doing the business. So then if we have a 25 meter cable, the money that I'm going to take in, if they sell that cable for $120 per meter, is going to be $120 times our length of cable, which is 25 meters. Okay, I'm actually going to take out my units for now. So this is just 120 times 25. And then I'm going to subtract the amount that I have to pay, which is 6 root x dollars per meter, but that's constantly going to change based on what x is. So for that, I need an integral. I'm going to add up the total as x changes from 0 to 25 meters of 6 square root x. And that should give me the profit. Okay, so they did ask us to actually find it, so I need to go from here and actually solve this. So let me go ahead and rewrite this square root as x to the 1/2 power. Oh, 6x raised to the 1/2 power. Which should make this easier to integrate. So if I integrate this now, I've got our profit is 120 times 25 minus, if I integrate 6x to the 1/2 power, I'll get 6x to the 3/2 power times 2/3. Did it again. Okay, 6 x raised to the 3/2 power. There we go. As x changes from 0 to 25, okay, so then I need to plug in my upper bound and subtract my lower bound. So this will be, just copy from the last one then. If I plug in 25, then I'll have the square root of 25, which is 5, cubed is 125. My 6 and my 3 will cancel, so this is 4 times 125. And then if I subtract, when I plug in 0, I get 0. Okay, so I've got this so far. And I'm going to group this a little bit differently as well. So if I wanted to pull out a 5 from the 125, then I would get 20 on the outside times 25. Which will make this a little bit easier to solve by hand. So now I've got 120 minus 20 is 100 times 25. Or 2,500 USD. Okay, any questions on A? Okay. So then the next thing they want us to do is explain the meaning of the integral from 25 to 30 of 6 root x dx in the context of this problem. So you'll notice we use that same integral with different bounds for our money out. So this is actually the cost that the company has when they produce the cable. So from 25 to 30 would be the difference in the cost to the company of making a cable that is 25 meters versus a cable that is 30 meters. So I'm going to write that out in a sentence really quick. This is the integral of 25 to 30 of 6 root x dx is the difference in the cost. Okay, let me put myself on normal type really quick so I can do this a little bit faster. There we go. Okay, is the difference in the cost in producing a cable that is 30 meters long and the cost of producing a cable that is 25 meters long. Okay, I can't really see what I did there, so I'm going to put this down to another line. In US dollars. Okay, I think that one was pretty straightforward, so I'm going to jump to C. I want to write an expression involving an integral that represents the profit on the sales of the cable if the cable is k meters long. Okay, well we just did profit on the sale of a cable that was 25 meters long. So the only thing I'm going to do then is I'm going to copy our equation for the profit at 25 meters. And we're just going to change 25 to k. Oop, 25, I want to change to k. There we go. So the cost to the customer is 125 times k, so that's the money that the company is taking in. And then the money that the company is spending depends on the length of the cable, which increases based on how long that cable is, from 0 to k. Okay, last step. They want us to find the maximum profit that Mighty can earn on one sale of the cable. So in order to maximize a value, I would need to check the slope, set it equal to 0, and solve for x. Because any point where the slope is 0 could be a maximum or it could be a minimum. So the first thing I'm going to do is derive this equation for profit that we just found. So let me copy my equation really quick. So if I derive this, I'll say the derivative of profit is equal to 120 minus, if I derive this integral, that's second fundamental theorem, so I'll have to plug in k. So that would be 6 root k. 6 root k times the derivative of k, which is 1. Minus my lower bound, which is 6 root 0 times 0, which is 0. So my derivative of profit is just this. 120 minus 6 root k. And then I'm going to set that profit, or I'm going to set the slope of profit equal to 0 and solve for k. Okay, so if I do that, I'll have something like this. Uh, 6 root k is equal to 120. Therefore, if I divide both sides by 6, I have the square root of k is equal to 20. Therefore, if I square both sides, k should be equal to 400. So this is our only critical point, but I'm not quite done yet. Because we have not proven that it's a maximum. So there's two ways I could do that. I could either do a first derivative test or a second derivative test. We have two options for proving that this point is a maximum. Our two options are a first derivative test or a second derivative test, which would look something like this. A first derivative test proving that before 400 the slope increases and after 400 the slope decreases. Would show that at 400 must be a maximum since the slope is 0. If I have a point where the slope is 0 and we change from increasing to decreasing, then that must be a maximum. So if I plugged in 2 points that were around 400, it really doesn't matter what points you pick since this is the only critical point. Then I could prove that this is a maximum point. So that would look something like this. My derivative of profit at the point, we'll do 1, is equal to 120 minus 6, or 114, which is positive. But my derivative of profit at easy number to take the square root of, let's do let's do 10,000. Okay, would be 120 minus 6 times the square root of 10,000. So I was just looking to pick a number bigger than 400 there, but I thought 10,000 would be easier because the square root of 10,000 is 100. So this would be 120 minus 100 times 6, which is negative. So that's negative 480. Therefore, our profit is maximized when the length of the cable is 400 meters. Okay, the other way that I could have proved this was with a second derivative test. If the concavity of our profit is concave down at the point when the slope is 0, then that point is a relative maximum. If I'm concave down with a slope of 0, then it must be a maximum point. So if I derive this profit equation again, I'll get this. The first derivative of profit was that, so the second derivative of profit then is going to be, if this is, I'm going to rewrite this square root here. This is k to the 1/2 power. Okay, so if I derive it again, I'm going to multiply the 6 times the 1/2 to get 3. K to the negative 1/2. Or if I wanted to rewrite that, I could say this is negative 3 over the square root of k. I think I might just have to rewrite this. Negative 3 over, there we go, root k. Okay, and then if I plug in our k value, which was 400, I can figure out what the concavity is at that point. So I could say the second derivative at the point 400 is equal to negative 3 over square root of 400, or negative 3 over 20. Since that's negative, we are concave down. So since our profit is concave down with a slope of 0, when the length of the cable is 400 meters, profit is maximized. The length of the cable is 400 meters. So those were our two options that we could have used to do that. Okay, any questions on what we did? Oh. Okay, I've got your mic out again, so if you do have a question, just type it in the chat, and I should be able to see it in the chat. Alright. Check to see if anybody's joined really quick. Nope, still us. Okay. So next one. We did question 4 last night. Oh, no, we did 5. Okay, so we'll do question 4 then. So I've got this region R enclosed by two graphs of y equals 2x and y equals x squared. So the top graph then is the line, so that's going to be y equals 2x. The bottom graph is the curve, so that's going to be x squared. So for the first one, we want to find the area of R. So if I want to find the area of R, I'm going to do my top curve minus the bottom curve. So I'm going to do area R is equal to my top curve, which is 2x. So let me integrate really quick. Okay, I'm going to integrate as x changes from 0 to 2, because they were nice and actually gave us the point without having us having to have us solve for it. If they didn't give us that point, I could have set 2x equal to x squared, and then solved for the point where they intersect. And that would have given us that point too. So as x changes from 0 to 2, I'm going to subtract 2x minus x squared dx. Okay, they do want us to find the area, so I am going to have to solve this. Rewrite this as area. Okay. So if I wanted to solve that, I'm going to go ahead and integrate this. So this is going to be 2x squared over 2, which is just x squared, minus x cubed over 3. As x changes from 0 to 2. So I'm going to plug in our upper bound and subtract our lower bound. If I plug in my upper bound, I'll have this. So when I plug in my upper bound, I have 2 squared minus 2 cubed. And I actually don't need to plug in my lower bound because it's 0. And if I plug in 0, I'm going to get 0. So this is going to be 4 minus 8 cubed. Sorry, 4 minus 8 over 3. Almost midnight. So I can get a common denominator, and this will be 12 thirds minus 8 thirds. Or 4 thirds. Okay, I'm going to go ahead and make this another line. So this was area. Alright, I've got space, so I'm just going to move all of these down. Okay, so my area is 4 thirds. And I do not believe we were given units, so that's as much as we can do. I'm going to double check that. Okay, we don't have units, so that's as much as we can do. So for the second one, I'm told that the region R is the base of a solid, and then for each solid, the cross-section perpendicular to the x-axis has this crazy area. Find the volume of the solid. So in general, volume is equal to a 2D area times height. So I could say that if I had cross-sections perpendicular to the x-axis, that would look something like this. Open a new tab here, not this one yet. Crops that. Okay, so I've got cross sections that are perpendicular to the x-axis this time. So something like this. And those cross sections are popping out of the page based on what a sine function would look like as that function changes. So it would look something like this. Where I've got a crazy cross-section popping out of the page that's not quite a regular shape like we're used to, but is some sort of a curve. A little bit exaggerated, but you get the idea. So crazy curved shape that's popping out of the page. But my cross-section is perpendicular to the x-axis. So what that means is I've got two sides for this. I believe I was told that they were squares, but I'm going to jump back and double check. Okay, we actually don't know. We were just told the area, which is even better. So I know that the area here in yellow is given. And then this width that I'm going to mark in blue is my change in x. Okay, so I've got a width in blue, which is my change in x. And I've got an area in yellow that was given as my function. Okay, so if I multiplied area times this change in x, I would get the volume of the shape right now. And if I kept doing that as x changed from 0 to our next intersect at x equals 2, then I would stack up all possible areas together and get the volume. Okay, so we're going to do that. So the picture was a lot more complicated than just writing this out, I think. For this one, area was the sine of pi halves times x. So I'm going to integrate as x changes from 0 to 2 of the sine of pi halves x times dx, which would be my height. Okay, they do want us to find the volume, so I am going to actually integrate this. Okay, if I integrate sine, I'm going to get negative cosine. It's not the full story yet, though, because I do have an inside function of pi x squared over 2. Sorry, pi x over 2. So if I was deriving, I would need to multiply by pi over 2. So if I'm integrating, I need to do the opposite and divide by pi over 2. But dividing by pi over 2 is the same thing as multiplying by 2 over pi. So that's what I'm going to do there. So that's my extra part that I have because of chain rule. And then we do have bounds for this integral, so I'm going to put in my bounds really quick. I want to plug in my upper bound and subtract my lower bound. So I'm going to plug in 2 and then subtract what happens when I plug in 0. I do need to be a little bit careful here. Even though one of my bounds is 0, I'm still going to plug it in because the cosine of 0 is not 0. So I do have to check both bounds. Okay, so then my volume is going to be equal to my upper bound minus my lower bound. So what happens when I plug in 2? Minus what happens when I plug in 0 into this entire equation, including that negative. Okay, so that's my upper bound minus lower bound. And then we can solve this. So my 2's are going to cancel. This is the cosine at pi, which is 1. So I could say my v then is equal to negative 2 over pi times 1 minus the cosine at 0 is also, oh, wait a minute, cosine at pi is negative 1. I just made a mistake. So let me go back and change that. This would be negative 1 times negative 2 over pi, so I'm going to lose this negative. Okay, minus negative 2 over pi times the cosine at 0, which is 1. So I've got negative 2 over pi. So this is 2 over pi minus negative 2 over pi is 2 over pi plus 2 over pi, or 4 over pi. And again, we don't have units, so I'm going to leave it just like that. Okay, last one for this set. I'm told that another solid has the same base as R. But for this solid, cross-sections perpendicular to the y-axis are squares, right? But do not evaluate an integral expression for the volume of the solid, which is kind of nice. So we don't actually have to solve the integral. We just need to set it up. So to set it up, I have cross-sections that are perpendicular to the y-axis this time, which are squares. So that's going to look something like this. So my side length here in red, which is my difference in my two x values of the functions, is also equal to the part that's popping outside the page here in blue. So that's also the difference in my x's. And then my width is my change in y then. So my integral is going to be in terms of y, not in terms of x. Okay, so if I set that up, I'm going to copy my picture really quick so that I've got it for the notes. It's going to look something like this. Get rid of this equation for now. And we'll crop this picture here. And wrap that through. Okay. Okay, I might have to go back and fix the edge of that later, but so that gives me this. In order to get that area, I would be multiplying my difference in x times difference in x. Since my volume is still area times height, I could say that, you write that out actually, volume is equal to area times height. I could say that my volume for this one is going to be equal to the integral Now this is in terms of y, so I'm looking at y values this time, not x values. This is as y changes from 0 to 4. Of my x values of the function, so that's x sub 1 minus x sub 2 dy, where x sub 1 is this far rightmost equation, and x sub 2 is the leftmost equation. Okay? Okay. So that's going to give me this. This rightmost equation was my x squared. And this leftmost equation, I believe, was 2x. So I'm going to fill that in and then double check. 'Cause this was, our equations were, yes, x squared and 2x. Okay, now that would give me the y values though. So that's actually not what I need, because I need this to be in terms of y. So what I'm going to do is I'm going to resolve both of these in terms of y then. So this is going to be my I need the y values there. Let me just do this then. So this will be, not an equation. Y sub 1 is equal to x squared, and y sub 2 is equal to 2x. I'm going to solve for both of those in terms of y. So I could say that the square root of y sub 1, or square root of y, is equal to x. Sub 1. I need to put my subscripts here too. Y divided by 2 is equal to x sub 2. Okay. Double check over here, make sure I'm on track. I believe so. Okay, so I'm gonna need. I've got all sorts of stuff wrong here actually. So I actually need to square this. So I haven't made it a square yet. So let me square that really quick too. In order to get that area of the square, I would need to multiply base times height. So I need to actually square that. Okay, so then I'm going to resubstitute. So this is square root of y. And this is y over 2. Okay, and do we need to? We do not need to evaluate this. Okay, so we're actually done right there. So this integral should give me the total volume of what's going to happen if I stack a bunch of squares perpendicular to the y-axis from y equals 0 to y equals 4. And just add up all of those areas together. Okay, any questions on what we did for C? Oh. You're okay, alright. Was there a D? There was no D. Okay, so we've already done 5. So that leaves us with the last question, which is question 6. Just going to format this for the next people, and we'll go down and try that. Let's see if I can get that space in there too, so we're not overlapping. There we go. And we're good to go. So let's jump down to question 6. Last one. I've got a derivative of function f defined by this derivative. So I've got f prime is equal to g of x when x is less than 0. And I also have f prime is equal to 5e to the negative x over 3 minus 3 when x is positive. So I'm told that my graph is continuous for this derivative, which is shown, and that this derivative has intercepts at -2 and 3 ln 5/3. So the graph of g on negative 4 to 0 is a semicircle, and our start point at 0 is 5. Okay, so the first thing they want is to find all the values on which the graph of f has a point of inflection. So sorry. Okay, so find all the values where f has a point of inflection and then justify your answer. So in order to have a point of inflection, our second derivative would have to be 0, and the second derivative would need to change signs. So because I have a graph of the first derivative, I'm really looking at the slope of this graph. So slope of the graph of the first derivative. The slope of the graph of the first derivative is 0 when x is negative 2, and it does change from decreasing to increasing. I'm also changed from increasing to decreasing at x equals 0. So I have 2 points of inflection. So the graph of f has a point of inflection at x equals negative 2 and at x equals 0. As the slope of the graph of f prime changes sign at these x values. Okay. I may have misspoken there. I'm not sure because the chat's yelling at me. So for points of inflection don't need to have a concavity of 0 as long as we are changing signs. So it's okay to have a point of inflection at x equals 0. Okay. So then the next one, I'm looking for what is f of negative 4 and what is f of 4. So I think I'm going to go ahead and make a picture of this one too. So let me grab a bigger version of this for a picture really quick. And we'll work with that so that we can color. Okay. So if I was going to integrate f prime, I would need to get the area that's underneath the curve here in order to figure out our value at negative 4. So what I'm really looking for is this. I need this area here in yellow, which I'm drawing right now. Okay, so to get that area in yellow, what I'm going to do is I'm going to draw a box, since I know that this is a semicircle. I'm going to draw a box that looks something like this. Make that just a little bit wider so I can see it. Okay, so I'm going to get the area of all of this space inside the red box. And then I'm going to subtract all of the space that's inside the semicircle. So I could say area under the curve from negative 4 to 0 is area in red red box minus the white semicircle. Okay, so let me draw out all these areas then. So the red box is a 2 by 4 box, which means the red box has an area of 8. Then the semicircle has a radius of 2. So the area of the whole circle would be pi r squared, which is 4 pi. but this is only half the circle, so this area is going to be 2 pi. So then my area in yellow is 8 minus 2 pi. Any questions on what we did there? No. Okay. I believe that's all we need to do actually, because I've got a function for the other one, so I'm going to copy just that picture. Let's do this. I'm going to flatten, and we'll get rid of this part that we don't need over here. Okay. So that gives me this. Which I'm going to wrap again. Okay. So with that, I could say that f at -4 is equal to our start point. So I knew the value when f was 0 was what was given to us, I believe. Yeah, f of 0 is 5. Plus the change in our value as x changes from 0 to -4 of f prime of x dx. So I'm actually going to make this a general equation, since this is the same thing I'm going to do to find f of 4. And we'll write our general equation too. So in general, if I wanted to find any point, not just -4, I could say that the area, or my y value at f of x is going to be equal to my y value at 0, plus the change in my y value as x changes from 0 to whatever value x is. Okay, then if I wanted to find the area at -4, I know that my start point, f at 0 is 5. And because I've got my bounds shifted, I'm actually going to change this integral as well. So if I swap my upper bound and lower bound, that's going to multiply the integral by -1. So when I swap these bounds here, now I'm going from -4 to 0, and I can keep this positive area. Okay, and that will let me substitute. So this is, I can replace this integral with the area underneath the curve, which is the area we found in yellow, which is 8 minus 2 pi. So I have 5 minus 8 minus 2 pi is equal to f at 4. 5 minus 8 is -3, so I have -3 minus 2 pi. Should be f at 4. I'm going to double check and make sure we're on the right track again. I feel like I've got something. Oh, here we are. I miscarried a negative. There we go. Okay. So when I distribute that negative, that 2 pi should become positive. So I have -3 plus 2 pi. Okay, then the next one, we also needed to find f at 4, which is going to be 5 plus the integral from 0 to 4 of f prime of x. Only this time we don't need to find areas using shapes, because we were given a function, so we know the exact function. We can find the area under that. So I'm going to go ahead and integrate this directly. This is f prime of x between 0 and 4 is equal to 5e to the -x over 3 minus 3 is what they gave us. Okay, so I just need to integrate that. Okay, I'm going to zoom in because that's a little bit small. Alright. Okay, and I've actually run out of space for my function on that side here, so I'm gonna throw all of these on the right. We'll just work on the right side. So then I'm gonna keep going with this and integrate. So this is f of 4 is equal to 5 plus what I'm gonna get when I integrate this. When I integrate this, if I derive 5e to the negative x over 3, I would multiply by negative 1/3. So when I integrate, I'm going to do the opposite. I'll divide by negative 1/3, which is the same thing as multiplying by negative 3. So this is 5 plus, I've got negative 3 times 5 is negative 15, e to the negative x over 3. Minus 3x if I integrate. And I do need to plug in my upper bound and lower bound for that as well. Because even though my lower bound is 0 here, if I plug in 0 right now, I'm raising e to the 0 power, which is 1, and I will still get a value. So I do need to do upper bound and lower bound for this one. Okay, so now I can say that f of 4 is equal to 5 plus what happens when I throw in my upper bound, which is negative 15 e to the negative 4 over 3 power, negative 4 over 3rd, minus 12. And then I need to subtract my lower bound, which is negative 15 e to the 0 power, which is 1 minus 0. Okay, so I've got this. And if I add all of that together, I could say that f of 4 is equal to negative 15 over e to the 4/3 power. Oh, e to the 4/3 power. Because if I have a negative exponent, I can move that to the bottom of a fraction. Then I have negative 12 plus 15 is 3 plus 5 is 8. So 8 plus negative 15 over e to the 4/3 power should give me f of 4. And that's all they asked us to do. So I've got our two answers. I'm going to highlight in red because they're kind of hidden right now. So this is, I found f of 4 and I found f of negative 4. Okay. Last part of the last question. I need to figure out what value f has an absolute maximum and then justify the answer. So in order to have an absolute maximum, I would need to test the start point of my interval, the end point of the interval, as well as any points where I have critical points, because those could be those could be relative maximums. And if they're higher than my start point and end point, they will be the absolute maximum. So I've got all the critical points, which is whenever f prime is equal to 0, and the start point and the end point. Okay, so taking a look at our graph, I've got the start point and the end point, which is negative 4 and 4. Then I've got the points where this is equal to 0, so that's at negative 2 and about 1.5. So to find the absolute maximum, you need to consider the critical points and the start point and end point of the interval. So I have critical points at x equals negative 2 and at x is approximately equal to 1.5. And the bounds of the interval at x equals negative 4 and x equals positive 4. Okay, so I'm going to take a look at this really quick. So I need to see, is f prime changing from negative to positive or positive to negative will tell me if these are minimums or maximums. So at x equals -2, f prime is positive to positive for my y values. So that is not a that's not a minimum or a maximum. But at f prime or at x equals 1.5, f prime is changing from a positive to a negative value, so this is a relative maximum. So that means I need to consider this point here, and the start point and the end point. So I'm starting at our start point here at 5, I'm going up by this much, and then I start going down, so this end point will not be higher because I went down from my relative maximum. And then if I'm starting at 5, working backwards, because these areas are positives, I'll be decreasing. So if I work backwards from the start point, these areas would be negative, which means this start point is also lower than 5. Okay, so I could say something like this. Since f prime of x, that's our graph, was greater than 0, was positive, on the interval from our start point at x equals -4 to x equals around 1.5. I should probably get that exact x value, actually. I think I can do that, because we actually know the function for this one. So yeah, we should get the exact value for this. I know the derivative is equal to 5e to the -x over 3 minus 3. So before I go any further, let me set that equal to 0 and solve for x. So I'm going to move this whole problem down so I can see everything that I'm doing. There we go. So 0 is equal to 5 times e to the -x over 3. What's the rest of that? 5e to the -x over 3 minus 3. Okay, and I need to solve for x. So this is 3 is equal to 5e to the -x over 3, or 3/5 is equal to e to the -x over 3. So I can take the natural log of both sides. The natural log of 3/5 is equal to -x over 3. Multiply both sides by -3, and I have x is equal to -3 times the natural log of 3/5. Okay, we have... excuse me. We have a little bit of a problem here, because this looks like it should be negative, and actually it's not. So I'm going to use the power property of logarithms to rewrite this and show that this is not actually a negative value. So if I use the power property of logarithms, I can pull any number that's on the outside of the logarithm, and raise this number we're taking the logarithm of to that power. So this is the same thing as with the power property of logarithms. I'll do this on a separate line. X is equal to 3 natural log of 3/5 raised to the -1 power, which means I can take the reciprocal of that fraction. So I could say x is equal to 3 natural log of 5/3. Okay, I'm going to put that I'm going to try to put that 5/3 in parentheses so that I can use that later. I'm going to copy that then. Okay, so instead of saying around 1.5, I can say an exact number now. So x equals this, since that looks like that's going to be our answer. we'll get that exact value. Okay. So our graph of the derivative of x was positive from x equals -4 to x equals that point, 3 ln 5/3. And f prime of x is less than 0 on the interval from x equals the point we just found to the end of the graph at x equals 4. The absolute maximum of f must be at x equals that value that we found. Okay, I'm going to go to the graph one more time and explain what we just wrote out. So what we just said was, I'm going to use this one actually since we got the area written out. If I'm starting at 5, and we go backwards by 8 minus 2 pi, which means from x equals -4, I had to go up by a positive area in order to get to the y value 5. So that means the y value at x equals -4 is below 5. But from x equals 0 to x equals that point we found at 3 ln 5/3, there's a positive area, so we had to go up. So I'm going up even further than the value that I know is above my start point. Okay, so that means this point must be higher than all the points that came before it, because I was increasing. But then after that, we start decreasing, so my endpoint has to be below it. Okay, any questions on what we did? I'm going to write this out one more time in English. This means we were increasing from x equals -4 to x equals ln 3/5. Then decreasing until the end. Therefore, our highest points must be at the point where we stopped increasing. Like, means the exact same thing, but that might make more sense as far as English goes. All right. Thank you so much for coming. We are exactly on time right now, at midnight. Last day of the vacation. We do have school tomorrow. I will see you guys at 8 o'clock. Thank you. Goodbye.